Hello, everyone, and welcome to today's lesson. Today, we shall be discussing chemical bonding.
More specifically, we shall be focusing upon the subject matter of covalent bonds. This subject will include bond enthalpy, Lewis structures, resonance structures, along with bond polarity.
First of all, we shall draw our focus to bond enthalpy. Bond enthalpy can be defined as the enthalpy change that is associated with the breaking of a specific bond in 1 mole of a gaseous substance. The equation for bond enthalpy can be calculated by the number of bonds broken subtracted from the number of bonds formed. You can think of it as the opposite of Hess's law, as we take the enthalpy of the products this time and subtract it from the enthalpy of the reactants. The actual values of the amount of energy released or taken in when it is broken or formed can be found on a chart like this one. For bond enthalpy, when a bond is broken, the bond enthalpy is always positive because energy is required to break bonds. Meanwhile, when a bond is formed, the bond enthalpy is always negative because it always requires energy to form a bond. The larger the value for bond enthalpy, the stronger that bond is. Keep in mind that bond enthalpy is only for gaseous molecules and that the value used for these calculations are average values for the energy released. Also note that as the number of bonds that a molecule has increases, the shorter the bond will grow. Okay, now let's do a practice problem to see whether or not you understand the concept of bond enthalpy. Using a bond enthalpy chart, what is the bond enthalpy of the formation of gaseous water? Feel free to pause the video to do the calculations. Now let's go over the correct answer. First, let's start with the energy that would be needed to break the bonds between the 2 hydrogen molecules and the single oxygen molecule. Based off of the chart, it takes 432 kilojoules per mole for a single hydrogen bond. So multiply that by 2 because there are 2 of these bonds. Then add that to the amount of energy needed for the O double bond, which is 497, making the total 1,361 kilojoules. Next, calculate the energy needed to break the HO bonds. It takes 458 kilojoules per mole for a single HO bond, but the H2O molecules have 2 of these bonds and there are also 2 of H2O molecules. This means that you would multiply 458 by 4 to account for all of these bonds. Your sum should come out to be 1,832 kilojoules per mole. Then, simply subtract 1,832 from 1,362 to get negative 471 kilojoules per mole. And that is the bond enthalpy for the formation of water.
Moving on, we shall now go over to the subject of covalent bonds. A covalent bond is defined as a chemical bond that is formed by sharing a pair of electrons between 2 atoms. The overall electrostatic interactions in a covalent molecule are attractive with the electrons concentrated between the 2 nuclei of a molecule that leads to the 2 positive nuclei to be attracted to the center and helps to secure the molecule and prevent it from breaking apart. Usually, the 2 atoms will share its electrons in a single covalent bond or single bond. But some molecules share more than 1 pair of electrons in order to achieve a full octet of electrons around the atom. This usually leads to a double or triple bond. In a double bond, 2 electron pairs are shared, while in a triple bond, 3 pairs are shared. Covalent bonds are formed between 2 nonmetals because the difference in electronegativity is too small to be ionic. Keep in mind that when a covalent bond is formed, both elements are trying to satisfy their outer shell of electrons. Typical characteristics of covalent compounds are low melting and boiling points, non-conductive, both amorphous and crystalline structures, and are usually gases or liquid at room temperature, although there are exceptions. Now, onto bond polarity. Bond polarity can be defined as the measure of how equally or unequally the electrons in any covalent bonds are shared. There are two types of covalent bonds. Non-polar covalent bonds, which are bonds in which the electrons are equally shared, and polar covalent bonds, in which one atom has a greater attraction for electrons than the other atom in the bond. The ability for an atom to attract electrons to itself is called electronegativity. When talking about solubility, just think that like dissolves like. Thus, polar liquids will dissolve other polar substances, while non-polar liquids will dissolve non-polar substances. This is the reason why oil separates from water, because water is polar and oil is a non-polar hydrocarbon.
Okay, now we are going to differentiate which bonds are more polar than others. For example, if we have two bonds, BCl and CCl, which will be more polar? Feel free to pause the video to think it out. So if we walk through this problem, we know that the chlorine atom is similar in both atoms. Thus, that leaves us comparing the electronegativity of the boron and carbon atoms. Boron has a lower electronegativity than carbon, and chlorine has a relatively higher electronegativity. As we have stated before, the larger the difference in electronegativity, the more polar the bond. So to conclude, the BCl bond is more polar because the difference in electronegativity between the two bonds is greater than the CCl bond. Let's try another example, PF or PCl. Once again, go ahead and work it out. The answer would be PF, due to the fact that F is above Cl on the periodic table, creating a bigger difference in electronegativity, making the bonds more polar. Hopefully by now you have a clear understanding of the octet rule. However, that is not all there is to it. There are some exceptions. There are three main types of exceptions, which include 1. Molecules and polyatomic ions containing an odd number of electrons. 2. Molecules and polyatomic ions in which an atom has fewer than an octet of valence electrons. And 3. Molecules and polyatomic ions in which an atom has more than an octet of valence electrons. In certain molecule pairings, such as ClO2, NO, NO2, and O2 negative, the number of valence electrons are odd and cannot be completed like the vast majority of other molecules. Furthermore, there are molecules that are able to have less than a full octet of valence electrons. These molecules are more specifically known and seen as boron and beryllium. It is not mandatory for these atoms to complete their shell with 8 valence electrons, such as with Bf3. It does not create resonance structures because that does not favor the high electronegativity of the F atom, and the dominant structure would be B with 3 single bonds and all 3 the Fs containing full shells of valence electrons. Finally, the largest class of exceptions remains with the hypervalent molecules, or species that have an octet with more than 8 valence electrons. Examples of these include PF5, SF4, and ICl4 negative. These are consistent when using atoms from periods 3 and below. The formal charge of an atom is the charge the atom would maintain if each electron pair was shared equally between two atoms in a molecule. To find the formal charge, you first need to count the number of all unshared electrons assigned to the atom, as well as count half of the bonding electrons that are assigned to each bond, or simply count the amount of bonding pairs of electrons. The equation looks like this. Formal charge equals valence electrons minus 1/2 bonding electrons minus non-bonding electrons. For instance, let's find the formal charge of the cyanide ion, Cn negative. Neutral C has 4 valence electrons, 6 electrons in the cyanide triple bond, and 2 non-bonding electrons. Therefore, it would be 4 minus 1/2 times 6 minus 2, which would equal -1. The formal charge of C is -1. On the other hand, N has 5 valence electrons, 6 electrons on the triple bond as well, and 2 non-bonding electrons. Thus, the formal charge of N is 5 minus 1/2 6 minus 2, which equals 0. We can then take the overall formal charge of the ion by adding the two formal charges, which is -1. Now calculate the formal charge of the nitrogen in the compound CH3CNH. The nitrogen has a triple bond with the carbon, as well as a single bond with the hydrogen. Thus, there are 8 bonding electrons. half of this is 4, and because there are no free electrons remaining, the formal charge is the amount of valence electrons of nitrogen, 5, minus 4, which means that nitrogen has a formal charge of 1.
In some molecules, the bonds represented by a Lewis structure are not actually the legitimate bonds in the compound. In fact, the truth about the bonds in those compounds are that they are actually an average of all the bonds in both strength and size. These structures are called resonance structures and are defined as structures that have the same placement of atoms but differing placements of electrons in the structure. However, we simply cannot draw half bonds in our Lewis structures, so in order to physically represent the resonance in a molecule structure, we must draw the structure of the molecule with every possible combination of bonds. For example, calculate the resonance structures that correlates to ozone or O3. Now, to start off, draw the Lewis dot structures for O3. Draw the 3 oxygen atoms and count out the number of valence electrons to be shared amongst the atoms. These 3 atoms overall contribute 18 electrons that are shared between themselves. Thus, one of the oxygen atoms has to be connected with a single bond, while the other oxygen atom must be connected with a double bond to fill the octet rule for all 3 of these atoms. If they were both only connected with a single bond, one of the oxygen atoms will only have 6 electrons, and thus causes the atom to fail to meet the requirements of the octet rule. Of course, now we come to a dilemma. We can choose to put a double bond on the first oxygen atom and a single bond on the second oxygen atom, or vice versa, and it would still work either way. This, of course, makes it impossible to describe a molecule using just a single Lewis structure, because it does not take into account the switching bonds. In the end, the 2 molecules are drawn side by side with a double-headed arrow in between to represent that the actual molecule is an average of the 2 structures. This means that, for this example, the bond that connects these oxygen atoms together have a length lying in between an oxygen single bond and an oxygen double bond.
Congrats! You have just finished the covalent bonding tutorial.
That concludes the section of chemical bonding. We hope you had a good time with this section and gained new insight into this fascinating subject. We have included a test down below in the description that you can take to test your memory retention upon this subject. We hope that you will have a great time with that too. Thank you for listening.